Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we're very pleased to have Jung-hee Chian visiting us. He's a professor at Seoul National University. Before becoming a professor at Seoul National University, he was also a postdoc at Brown University with Joe Silverman. Also held positions at several institutes in Korea, ITRI and ICU. He's also the winner of the Best Paper Award at AsiaCrypt in 2008. And today we're very pleased to have him speaking to us on some of his work on recent progress on discrete logarithm problems.
Thank you. Thank Christine for inviting me, and I'm so happy to give a talk in Microsoft Research. The previous title of my talk was the discrete logarithm problem with auxiliary inputs, but in this talk I'd like to introduce much broader topic, more top topics related to discrete logarithm problem rather than focusing on this only one problem. And mainly, can you hear me? It's okay. Mainly, I will introduce three topics. One is polar law algorithm on DLP, discrete logarithm problem, and another one is constraint DLP, and another one, the last one is DLP with auxiliary inputs. Let me start introducing discrete logarithm problem first. Yeah, here we restrict G to be a finite cyclic group of order Q generated by G, and then given an element of H in G, the discrete logarithm problem over G is to find an integer, usually the smallest non-negative integer, so satisfying G to the X is equal to H. And then X is called the discrete logarithm of H to the base G. And then this problem is popular in cryptography, used for key agreement, encryption, signature, lots of protocols. And in particular, finite fields are widely used to implement these DLP-based crypto systems, including digital signature standard, US standard for digital signature. And usually it's implemented on a subgroup, prime order subgroup of a finite field. And then for these problems, we have two attacks usually. One is an index calculus, and the other is polar law. Index calculus, the complexity of index calculus algorithm is determined by the size of P. The size P is the size of this finite field, and then the complexity of polar law is determined by the size of this prime order subgroup. In practice, usually P is taken to be 1024 bit and Q is taken to be 160. And we have several improvements for polar law, like including distinguished point method and R adding work, or some linear parallelization, and then speeding up using endomorphisms. But the complexity the complexity of the original algorithm, for the complexity of original algorithm, there have been no much progresses on the for several years, for several decades. Let me briefly recall the polar law algorithm, and then in polar law algorithm we consider iterative function f from a group to G, group G from to G, and then create a sequence G0, G1 through etc. And then here G1 is defined to be f G0, and then G2 is f G1, like this. And in that case, since G is a finite group, we must arrive at some collisions. Then there exists smallest integer mu and lambda such that G mu plus lambda is G mu. That is, you start from G0 and take F, G1, G2, G3, G4, etc. Then finally, some G mu is equal to G mu plus lambda. Then the row length is the length of this one. So it's lambda plus mu. This row length is the average of row length is square root of pi the order time over 2. Here the expectation the expectation is over the all functions f. So when we compute this row length for all function f, the expectation becomes this almost square root of the order. To be useful in discrete logarithm, the function f should be exponent traceable as well as random. That means if f can be expressed in the form like this, that is, when you are given an input of g to the a times h to the b, here h is the target element, then we should be able to know the exponent here. For example, f a random function f is when f is y square, and if you take this f, we know the exponent is 2a and this is 2b. So when we know the exponent of the input element, we know the exponent of output element with respect to g and h. The Pollard row algorithm, they start with the G0 with known exponent and then compute next element again and again using exponent trace function. Then when a collision is detected, we can find x because from these relations. Since we know if there is a collision from this equality, we know we can find the linear equation of x. And then it's not likely, with high probability, bi should be different from bj. And in Pollard suggested this function, and it takes more than the square root of pi q over 2 iterations. And R. Eddingworth gave us faster iteration, faster result. In R. Eddingworth, they used randomly chosen S points for R points. For example, R can be 20. That is, in 20 walks, we pre-select 20 points, and then given Y, depending on the y, we choose one of 20 points and multiply to get the next element. Okay, then how to once the collision occurs, we have to detect. If we store all the previous points, it's easy to detect the collision. But it requires square root q storage. It's too much. So instead of this, we use a very special method. For example, in fluid method, we store g to the I and g to the 2i for each I, and so they doesn't require any storage. And in Brent method, they compute g to the I for each I, but store only g to the 2k. So, for example, store G to the G sub 2, G sub 4, G sub 8, G sub 16, etc. But if there is a collision at some point, this collision is, you can find collision again and again. So finally, you can find the collision with G to the G sub 2 to the K. And the best method, actually, in practice, the best method is distinguished point method. Where is? Okay. DP is defined to be an element of G satisfying a certain condition which is easy to detect. For example, some LSB bit, some MS, for example, 20 MSB bit of GI is equal to 0. It's very easy to check. And then we store only this DP point. That is, we follow the random walk, and then whenever each point has 20 zeros in MSB, they store this. And then they, in each step, they compare each point with the DP, the elements in DP set. If it's DP, and then collision is detected after additional these steps at average. If theta is a fraction of DP in G, this is most convenient and then efficient. Okay, so my interest for this algorithm was how to speed up this Pollard law algorithm. There has been no much progress on this algorithm for several years, so we can consider 3 steps. One is to reduce the row ranks. How to reduce the row ranks? Since it depends on the random function, we should use some good iterating function, but it's not easy to beat the random functions with this a specific iterating functions. Another one is devise fast collision detection method. Fast collision detection after collision has been occurred, but currently the DP provide almost optimal method in the sense that this additional one is almost negligible compared to this. And third one is speed up each step. If we cannot reduce the number of steps, we can try to speed up each step of random functions. Okay. So let me introduce how to speed up each step. We call R adding work with DP method. In ith iteration, for given G sub I, we determine the index of G to the I. Usually, in Pollard algorithm, index is 1 over 3, 0, 1, 2, 1 over 3 element. And in 20 work, S is 1 over 20 values, from 0 to 19. And then first compute S, and then compute GI times M sub S. And if G sub I plus 1 is DP, it's stored in the table. And storing operation is not very frequent. So our question can be, is it necessary to compute the product at every iteration? Because what we need to know is only the index. And then the index is only few bit information. It suffices to compute just the index at each iteration until we reach a distinguished point. For example, we arrived at distinguished point once a million time, for example. So, except this DP, we don't need to compute this one. We might not need to compute this one. So that.
How do you tell if it's a distinguished point if you don't compute it?
Pardon?
How do you tell if it's a distinguished point if you don't compute it?
Yeah, but even for the distinguished point, we need to know only 20-bit MSB, not full element. Partial computation. That is, for example, we can consider 1024-bit finite field here. We need to compute 1024-bit for this element. Instead of this, we just compute 20-bit. Then 1 over million elements can be DP. Okay, and it's the idea is like this, and S is a index function from total group to R element. It's an index, and then we chose a random multiplier set. Let's see, it's a 20 element when R is 20. And we pre-compute of all product of L or less elements from M. For example, L can be 100. Any 100 product of these elements are pre-computed and stored. And then we define S bar, G to the L, and M to be the index of this multiplication. Okay, let me start from G0. And first, since we know G0, we compute as the index of G0. And then we can choose S1, the M as 0. And then if we perform the multiplication, we can now learn G1. But instead of taking the multiplication, we compute the index, this index. Let's assume we have a method to compute the index without multiplication when you are given 2 inputs. Compute the index, okay. Then until now it's successful, but we have a problem in the second step. When you compute S2, we have to S2 is the index of G2. G2 is the multiplication of G1 times MS1. But here, since we do not know the G1 element, we cannot, the S bar should be G1, MS1. But we do not know G1. Okay, let me see. S2 is S index of G2. This is index of this one. But instead of this, we use, and this is okay. We did not compute this G1 element, so we cannot compute G1 MS1 since we do not know G1, but we have an identity. This is equal to this one. So instead of computing this one, we compute this one, and then MS0 times MS1 is taken from the memory. Since the L multiplication of the randomly chosen R elements are computed. Oh. So using these techniques, without computing the full multiplication for L steps, we can follow the random walks. And then after L steps, we exhausted the table. So we do full multiplication to compute G to the L, and then repeat this procedure. Yeah.
But isn't this way more expensive each step? Because you had to compute the multiplication starting from G0 every time?
This multiplication is pre-computed. So pre-computed. Because it will be done, it will be used again and again. And it's pre-computed. For example, if L is 100 and then R is 4, this size is just a kilobyte, several kilobytes, not so large. And whether it's efficient or not is depending on whether this index computation is faster or not compared with the full multiplication. And okay, then the remaining thing is how to detect the collisions. So rather than computing only several bits of information, we compute more larger information usually, 10 bits or 20 bits. And then anyway, G is more precisely, G is defined to be a distinguished point if the index is a fixed value and then certain number of starting bits of GI equal to 0. To check this one, we need actually more information. And whenever there is a chance of being some GI being DP, we do a full computation. Okay. So the question is, can we compute some bits of information from the multiplication without full multiplication? It's a very interesting question. And without modulo P, it's easy. When you compute a multiplication, if you know MSB of 2, X and if you know the MSBs of X and Y, you can guess the MSB of XY. Or if you know LSB of XY, you can guess the LSB of XY without regardless of other bits. But since the modular, it should be a modular reduction, we should perform the modular reduction here. It's more complicated, but still we can have more efficient one. That is, X is W is like a 2 to the 32, for example, word size. And then X is the summation of Xi W to the I, and Y is Yj to the, and W to the J. Then when you multiply two integers, you get 2t words. And then by taking modular reduction, you get this, for example, okay. You compute for example, if you multiply 1024 bit, it becomes 2000 bit. And then by modular reduction, 1000 bit can be moved here. You add. So to know the MSB, actually, it's enough to know the MSB of here and here. Okay, in this sense, let me omit the details. In this sense, if you have 32 words, if X consists of 32 words, you need to compute only one word. Okay, so we expect 32 times fast fast speeding up, but with some miscellaneous computations. Actually, this index computation is faster than 15 times faster than the full computation, than the full multiplications. And then when we apply it to the Pollard law, the comparison shows at least 10 times faster than the original Pollard law. So that is just as a summary, for finite field of size 1000 bit, our implementation shows more than 10 times speeding up. It's actually log p times speeding up in finite field. So, and actually, my goal was to apply this technique to elliptic curves. But application to elliptic curves requires to compute some bit of x over y modulo p without taking full modular division. But I'm not successful currently. I couldn't do that. So how to? We need to use Euclidean algorithm for computing x over y modulo p, but I don't know how to compute some bit of this information without computing full, recovering full element. For example, whether this element is quadratic residue or not could be not one bit information. But even for determining this element is quadratic residue or not, it's hard when x and y are a little bit complicated, like elliptical operations, including, plus. Yes.
That little x and that little y, are those coordinates of the?
Okay. For example, when the more precise question is like, given x1, y1, 2 point, the x coordinate of addition is like something like this. We want to determine whether this is quadratic residue or not. If we have a fast method to determine this is quadratic residue or not, then efficient then computing all the element itself. I spent some times, but I was not successful. And then one of the comments is when I do these computations, the alternate to get the best way to get some information is to use Montgomery reductions, and then that gives the good way to compute some bits without full computation. But I couldn't generalize into divisions. Division is too hard compared with multiplication. I learned this lesson in this age. Okay.
The reason that you wanted the division was because the distinguished point. What's the analog of the distinguished point method? It's if you want to check if something's a quadratic residue. So
yes, if it's quadratic residue, we follow this direction. For example, the simplest random walk is like 2 directions random walks.
Oh, so I see. So your x over y there. The x is the numerator, like
yes.
y2 minus y1. And, I see.
Sorry. So if we have a method, we can speed up the Pollard law on elliptic curves. That's one of my goals to do. Any questions?
tables went for up to L elements, but L being like 70, 2 to the 70, it seems a lot of memory.
Not exactly, because we implemented 4 adding works. Then, rather than, for example, 4 to the L, we don't care about the order. Okay, so we should choose what is it's the allow the ignore the order. Okay. The table contains how to say? We take from M, L element, and multiply them. Then that means we choose L element without order, and then it's much less than this one. I'll give you the number after this talk. Yeah. Any question? Any other questions? Okay. Next, let's go to the next topic. And constant DLP. We can let's consider DLP on a group G of prime order P, and weight T is the Hamming weight of binary representation of T. So, for example, the weight of this one is 3. And then Hamming weight T DLP is like this. Given Y and G, compute the discrete logarithm whenever the weight is T. Weight of the exponent is T. In a group with fast endomorphisms, for example, binary fields or Koblitz curves, the doubling is fast, so the cost of exponentiation mainly depends on the weight of exponent. In binary field, the weight should be a the Hamming weight of binary representation. In Koblitz curve, it should be a Hamming weight of phi-adic representation. Okay. So we working with an exponent of low Hamming weight has advantage that the exponentiation is faster than the with randomly chosen x. And so there have been several proposals using this low Hamming weight DLP. The question is it safe? Does it have the same strength of the same complexity with the ordinary DLP? That means, can we apply baby step, giant step efficiently? And then let X be the set of integers less than Q with Hamming weight T. Oh, sorry, it should be order P. It's P. And the question is, find two sets A and B of size square root Q, such that X is covered by A minus B, modulo P operations, or A over B. Then, if G, an element of X, is represented as a minor difference of X and Y, and then when H is given, then we check H. Okay, replace G by X minus Y, then we obtain this one. So we check this equality after making a table for G to the X. So the complexity depends on the size of A and B. Then the complexity is added, not rather than multiplying. That is, the complexity is square root Q. And also, if it's similar when G is represented as a ratio of X and Y. We raising a power of Y here. So H to the Y is equal to G to the X. So also we can apply baby step, giant step here. So the question is how to find A and B of size square root Q. And then the answer was given by Coppersmith and later Stinson. It's called splitting system. How to find A and B. Okay, this problem was generalized into low Hamming weight product. In that case, they use product of two exponents of low Hamming weight rather than one. It was proposed by Hofstein and Silberman. And then it looks very efficient. It provides very efficient exponentiation for Koblitz curve case. And then how to attack this? If x is equal to x1 times x2, it's very easy to split like this. So to get more complicated DLP, we should have x2 is much greater than x1. It's not balanced case. And here x is the set of positive integers of Hamming weight Ti, and then x1 is chosen from x1, capital X1, and x2 is chosen from the capital X2. In this case, we need to have more flexible splitting system. That is, you split x into A and B, but some set is larger than this one, and some set is smaller than this one. So we worked on this. It's called parameterized splitting systems. And then so we found more efficient attacks for this exponent than suggested, but still we do not know which one is the optimal complexity. That is, let me here several further questions. Here we do not have a memory efficient algorithm for this algorithm. We have only baby step, giant step style. That is, we don't have a Pollard law style algorithm for this one. And then to use this exponent for some protocols, we need to have a lower bound of the complexity. The first step of this is to have a cardinality of the multiplication. But even for this, we don't have any information. That is, what is this? So there could be several repetition for x1, x2 modulo p. So compute the lower bound on the cardinality of this set would be an interesting problem. If we have a good bound for this, we may use this exponent for some lightweight device. In 1977, Erdos and Newman suggested a question like this. Is there any set S whose generic DLP complexity is much greater than square root S. And then it holds for random set S, but the answer was given by Mironov, Mityagin, and Nishim in 2006 in Ant. They gave a construction of such set S. This is another lines of research related to DLP. Any questions? I'm making everybody sleepy. Yeah.
This is just an aside. Very recently, all three of those authors were all Microsoft employees.
Oh, all?
Mironov, that's Ilya, and Anton Mityagin was here, and then Kobe Nisim is in Israel.
Yeah, we expect more fruitful result about this. And the reason I'm interested in this topic is I want to design some lightweight protocol which can be used for example, RFID and some sensors. Then this low Hemingway product is a good candidate. But the problem is, as I said, there is no bound, no ground for the complexity of these problems. We don't have attack. And my attack is just the improvement of the attack suggested by the authors. But so the research about this could lead to an efficient cryptographic protocol can be used to some lightweight device. Okay, let me move to a third one. We know RSA problems, and we know DLP, but usually the crypto system does not depend, whose security does not depend on DLP, rather than but computational Diffie-Hellman problem or decisional Diffie-Hellman problems. And nowadays, we are relaxing the problems more and more. Why? To design a new system with additional properties like ID-based encryptions or some attribute-based encryptions, etc. Or to prove the security without random oracles, we need relaxed assumptions. Okay, how to relax? We have two approaches. Okay, let me consider this. How to get a good grade in examinations? We have two ways. One, grading should be flexible. And okay. Then another one is give more hints before the test. It's similar in our situation. Then relax the problems. By flexible gradings. For example, flexible RSA problems, given a composite N and message M, in the classical problems, we need to the solution should be M to the 1/3, right? But it's okay. It's okay for any E. That is the flexible or strong RSA problem. And we have a variant of DLP with flexible grading. So, for example, it's LRSW problems. It was used for anonymous credentials. Then we have flexibility for H. Right? Actually, if H is fixed to G, it's the same with the Diffie-Hellman problems, but they allow to use any H here. Another direction is to give more hints. For example, when you are given G and G to the alpha, if you can compute g to the 1 over alpha, it's called Diffie-Hellman inversion problems. But instead, this we give more hints like g to the alpha square, g to the alpha cube, g to the alpha to the L. This problem is called L-weak Diffie-Hellman problem. And we have several. It was proposed to design traitor tracing scheme. We have more variants like given this. When L is without this is the same with Diffie-Hellman square exponent problem, but we provide L elements and then ask to compute g to the alpha to the L plus 1. It was used to design short signatures with random oracles and short group signatures. And also we can apply this variant to pairing settings. And then given up bilinear maps, okay, we can ask to compute this quantity, the ID-based encryption, verifiable random functions, and then hierarchical ID-based encryption with constant size ciphertext and publicly broadcast encryption, etc. These days, these problems are very popular, and then based on these problems, many protocols are proposed. And all of them has auxiliary inputs like D input. Questions, the natural question is, are they as hard as a DL? In generic model, they provide the complexity of strong DL, or let me call this one is discrete logarithm with auxiliary inputs, or sometimes strong DL. Actually, it's not stronger than the DL, but stronger assumption. So to avoid the confusion, let me call just strong DL. The complexity is lower bounded by square root P over D group operation when D is not so large. It was square root P for the DL. So the natural question is whether this bound is optimal in generic model. That means can we devise an attack whose complexity matches with this lower bound? Okay.
So whose result was that there was the lower bound?
Oh, it's by in the first paper by Bonnet et al. When they proposed these L-strong problems, and then later, whenever they propose some new problems, it becomes mandatory to prove the generic complexity in appendix. Yeah, lower bound.
In the generic.
In generic model. Yeah, generic group model.
Okay.
In appendix. Okay, so for this algorithm, we use baby step, giant step techniques, and then given H, G to the alpha, we split alpha to be U part and V part, and then M is square root of P, and then move, then, okay. Oh, cannot see. Maybe it's better. Okay, so this equation becomes this, and then we construct a lookup table for the left and entry, and sort it by the first component, and then compute G to the B and compare with the first entries in the table, and requires square root P Trojan computation. And we apply this technique to the strong DL, but in some for the exponent only, for the exponent, that is, let zeta be the generator of GP star. We work the the point here is we work on the exponent rather than group itself. We apply the baby step, giant step technique for the exponent. Here, that is, you are given alpha, and let's assume we are given alpha and alpha to the d, even though we do not know this quantity. And then let zeta be a generator of GP star. And then zeta head is defined to be zeta to the d. And here, alpha to the d is order p minus 1 over d. And thus generated should be generated by zeta hat. And we compute g such that this alpha to the d is equal to zeta hat to the g. If we can find g, then we can find beta. But it's strange because we do not know beta itself. We know g to the beta, but we do not know beta. So how to check this equality? But we can check this equality by raising power like this. We know g to the beta. So, and then since we know zeta hat and then zeta hat to the g, we can compute this one. We check this equality. And then when we have a collision, then beta should be this quantity. Okay, that is, rather than working on group G, we working on group exponent group GP. But only the equality is checked in the base group. And then here we apply baby step, giant step technique to speed up. That is, rather than checking this one, we check this. Because in this case, it's fixed. And then this part, right-hand side part varies. But if we varies two sides, simultaneously, we get the complexity becomes square root. Okay. That is the idea and then algorithm itself. And then once we compute, we know beta, using similar techniques, we can recover alpha again. Okay. And then when p plus 1 has a, this attack works only when d is a divisor of p minus 1. Otherwise, for example, if d is a relative prime to p minus 1, this is the order of p minus 1. So doesn't reduce the complexity. So d must be a divisor of p minus 1. And what if p minus has no small divisor d? So in that case, we can use p plus 1 or more generally p to the n minus 1. But the idea is the same, essentially the same, but here we have to use more mathematical notations. So for example, let H be a subgroup of order p plus 1. Of the multiplicative subgroup of f p square finite field. And then we can consider this finite field as a vector space of with two copies of GP, vector space of dimension 2 over GP. And then we embed alpha to alpha bar in a group H. Okay, the purpose is we embed to we embed alpha to a smaller group H. And then the alpha bar to the D, here H is order P plus 1. Alpha bar to the D is the order of P plus 1 over D. Yeah? That's the point. it's not a map, just embed to alpha bar, and then alpha bar is an element of H anyway. And if you raise to the power of D, since D is a order divisor of P plus 1, alpha bar to the D is the order of P plus 1 over D. Then we use some baby step, giant step technique to recover beta in square root 2 P plus 1 over D times. But to apply these attacks, P minus 1 or P plus 1 should have small vectors. When I checked all the known parameters, they are susceptible to this attack. That is vectorized P minus 1 gives enough small vectors for these curves, elliptic curves. And so if we apply this one, for example, and elliptic curve, for example, in BGW broadcasting encryptions, they use these elliptic curves, and then by Pollard law algorithm, the complexity is 2 to the 76 elliptic curve operations, but it reduced to 2 to the 59 exponentiations when n is 2 to the 32. And its number of users. If they use a billion users, it reduced to this one. Okay.
That means 4 billion users have to collude to break the system?
No collusion.
Okay.
To be used for n users, they have to publish the n public keys. This is used, and then usually they preoccupy some to. Okay, for the future, they usually take large n. So that's why they consider these unbelievable numbers.
So that n is your n is the same n users.
N users.
The size of the small factor is like 2 to the 17 or something.
2 to the 76. Pardon?
What's the size of the divisor? The divisor of the group order is like
Divisor of
17 bits.
The group order is 151 bits. The group order is P. I didn't write down the factorization of P minus 1, but the P minus 1 has enough factors, enough large, small factors. We can choose as we want. And, okay. Yeah.
Can you go back to slides, please? So, so maybe back again. Sorry, can you go back to? Okay. So your method is working here right now in Z star P, right? Mm-hmm. Your method is working in Z star P, and G is a generator of Z star P.
Yeah.
What happens in a prime order group?
Prime order group.
Yes.
It works prime order group P. Prime order P.
Right.
But P minus 1 is not prime.
Right. But what happens in a prime order group?
Pardon? I'm working on prime order group.
Right. But the order of G is P minus 1.
No. P.
Oh, okay.
P. But we consider P minus 1. I think we'd better have some good names for this. It's something like this. We have two double exponents. So here, G is group G, and the alpha belongs to GP, but this belongs to GP minus 1.
Okay.
Yeah.
So this type is actually in the exponent.
Yeah.
Okay. So I mean, I was wondering, I mean, do you really need to know the order? I mean, does your method work, for instance, in a group of unknown order?
Unknown order.
Yeah, I mean, where you have an approximation of the size of the order. I mean, do you really have to know precisely the order of the group? Or you can adapt your method to work in a known or unknown order?
That's very good question. That's very interesting, but let me give some time. And I couldn't answer it currently. Yeah. Yeah, that would be a very interesting question. Okay. So as a summary, when you are given D element, D plus element, if this divisor of p minus 1, the complexity is reduced by square root d. And then if this, it holds also when this divisor of p plus 1. So in this case, we have almost matching attack for the generic complexity. But we have a prime p such that both p minus 1 and p plus 1 are almost prime. So we couldn't find appropriate size d, divisor d. In that case, it's still safe. And then the ratio, the proportion of such primes are are very large. I mean, the more than the susceptible primes. So we need to generalize this attack too. We have more rooms.
What are you saying? What's the percentage? Do you know the percentage of the time that those two are both almost prime?
It's non-negligible, but it's not
Very small.
It's very small. Okay.
Naively, it would be 1 over log squared p. If you assume primality is a random process, which it isn't.
Yeah, it makes it a lot harder to generate suitable curves. If you have to satisfy both those conditions, it makes it a lot harder to generate suitable curves. Because you have less flexibility for the CMF.
Yes, makes it harder, but still possible. Still possible to generate the elliptical parameters to resist these attacks. So that means even though you use strong discrete logarithm assumptions, you don't need to increase the key size. If you take a good prime P, safe prime P, but currently there is no guarantee whether this prime is strong or not. Just resist against these attacks. So it would be better to avoid to use these assumptions with the same key size. I mean, we need to increase the key size when our assumption is strong Diffie-Hellman rather than just Diffie-Hellman. Okay, but my interest is to generalize these attacks. Sato tried to generalize these attacks to matrix group, but the complexity is not lower than the previous. And time's over, okay. And let me introduce this slide only. And then I found some generalized algorithm, but the complexity is still under review. And we embed alpha to fp to the n rather than fp square. Okay, then let p to the n minus 1 is t times e, and zeta be a generator. Then h be the subgroup order d. Here d is a smaller element, an integer smaller than p. Order p generated by zeta hat. Zeta hat is defined to be zeta to the e. And then we still embed embed alpha to alpha bar to this element and raise its power additional with some random factor r, then the point is this is an element of order D. Here H is the subgroup order D. Our objective is to embed an element to order D element, order D group. Then using the similar method, the complexity becomes square root D. Since D is less than T, square root D is less than square root P, it becomes more efficient attack than the usual disk log attacks. So we have this embedding. If R is relative prime T, D, let me omit the details. And then, but this embedding is successful, but to have another factor is, okay. The problem is, since alpha is a linear function of alpha, alpha bar is a linear function of alpha, this is a linear function and then with exponent RE. So it's a polynomial of degree RE. Degree RE is too large. You know, RE can be larger than P. too large. So we should be able to make small. This one, here we use some technique. Let's consider a periodic representation of RE. Then, okay, RE is written as a summation of EI to the P to the I. Then we know since P is a characteristic, P come into this part. And P. And then finally, this times RE gives smaller degree rational functions than the RE. Due to RE, since RE is, if we consider periodic representation, purely representation of RE. So using this, if sum of signed digit of RE is small, this attack is successful. That means, okay, let me introduce the sum of digit. What is sum of digit? Given this element, we expand as a PRE element. And then if all the coefficient EI is positive, sum of digit means just this element. But sum of signed digit means we take maximum of positive coefficient and my negative coefficient. And they determine this is the degree of the numerator and then denominator, and then this determine the degree of numerator. So if the sum of signed is small, this beta is a rational function of smaller degree. Okay, so using similar techniques, we have the algorithm for strong DL. Let me introduce the attack scenario. Suppose a prime P, we are given prime P and then they are given. And find an appropriate divisor D of P to the n minus 1 for some n. We try from n is 1, 2, 3, 4 for small n. And then if we find the appropriate divisor D, then next we try to find R such that sum of digit is small. In this case, we can use lattice LLL reduction and then apply the algorithm to recover alpha. And then complexity depends on this one. And as a further study, I'm still working on how to find the R such that the sum of digits is small. I know how to find the R such that sum of digits is small, but I need to impose this condition also. And then another question is how to check if some prime register against this attack, because there are many attacks here. It's not easy to guarantee this prime is strong enough. When we use strong DL assumptions, the designer wants to claim, this prime is enough. It has this security. But in this case, it's not easy to say. But we can say we can use the lower bound of the generic complexity. But other than this, we don't have any ground. And then another question is, given the strong DL element, the complexity is always reduced by sqrt D. That is, we have a matching attacks for arbitrary prime P. That is our questions. Also, these days we have many flexible assumptions, some linear assumptions, many assumptions. I think we have more designers than analysts these days. So we are lack of analysis of these assumptions. We need to investigate the security of complexity of these assumptions. And then, so we may consider embedding to elliptic curves either. It's related, but we still have some problems to embed elliptic curves. If we are succeed to this, we can say the strong DL has strong DL has the complexity reduced by sqrt D from the ordinary DL, but it's still it's not successful yet. Okay, that's it. Thank you for your attention. Yeah.
I'm still curious about your method. You showed a giant step in the exponent. So what happens if you use a group of order a safe prime? Like a prime P that is written as 2q plus 1, where q is also prime.
Yeah.
What happens if I change the assumption where I use only quadratic residues in the exponent, so that there is no divisor because
If P is, for example,
2q plus 1, yeah.
And it registers against my P minus 1 attack, but it can be susceptible against the P plus 1 attack. So it should simultaneously of the form like this, or you can allow some larger cofactor rather than 2. But it exists, and then some people generated this prime.
So it will resist the attack.
The attacks. But if my new attack is successful, then cannot avoid.
But every extra condition you put on there makes it could end up making it impossible for you to generate a group of that order, because to generate an elliptic curve of prime order is already hard, and then if you put extra conditions,
right,
you might end up not being able to get one.
Increase the parameter generation time to 100 or log p times.
Generating set prime is not.
No, but generating an elliptic curve with a certain order. Then
But if it's a matter of getting 10 curves every 10 years from NIST, right? There's plenty
Yeah.
of computers are available for that kind of job.
Yeah, but the size of those Hilbert class polynomials is like, if square root of d is like square root of p, like if p is 256, so square root of d is, like 128. The size of the polynomials is like e to the square root d. That's just the size of the coefficients of the polynomials. So that's why it's hard to generate the curves. So I have a question. So even if you do that, then you also still have your other attack, which is a divisor of p to the n minus e, or minus 1. So if p to the n minus 1 is d times e, how large of a factor can you use? Like d, reasonably, how much space or time does your algorithm take? Can d be 2 to the 40, or can it only be 2 to the 20, or what? How large is practical for your algorithm divisors of p to the n minus 1?
Yeah. Our algorithm depends on two factors, this one and this one, only two. And then usually the complexity of algorithm depends on this one.
And what is the complexity?
Square root d.
Oh, square root of d. Oh, okay.
Yeah,
So
and
you
then
can
the-
handle
yeah.
very large d, actually.
So if d is smaller than p, it can provide the more efficient attack than the attack of the ordinary DL attack. But the problem is this is related to DSDL, this element. If it's large, we need too many elements. It's not realistic. So we should be able to reduce this part. And then, that part is.
Did you find any of the NIST curves that are susceptible to this for some small values of n?
Not yet, yeah. Actually, yesterday I finished my setup of the Maple. Since I changed my laptop. Okay, maybe in several days I'm trying. The problem is current parameters are susceptible to this attack already, P minus attack. So does not give strong motivation.